So in this video, I'm going to go through the basics of how logic gates work. A logic gate works with a combination of either a 1 or a 0. So what does that mean? That means if you've got an electronic circuit, starting off at your positive, coming down here, this is a symbol for a switch. If we draw in a symbol for a bulb, coming out like so. If this switch is connected, so if we push this down, then electrons can flow, and that would be a state of 1. If there's no electrons flowing, it's going to be a state of 0, so the light bulb won't turn off. So computers won't turn on. Computers are made up of loads of 1s and 0s that make the whole thing work. So using logic gates, we can decide whether an output is going to be 1 or 0. So I'll show you what that means. So the first logic gate I'm going to introduce to you is an AND gate. How does this work? Well, could you imagine if we had a coffee machine and you had to put in a coin and you also had to press a button to get your coffee out. So if we're going to press a coin in will stand as a 1, no coin in will be a 0. So if I was to put in a coin, and if I wasn't to press the button, you can imagine that I won't get any coffee. So my output will be 0. Now if we change this, if I was to not put in a coin, but I was to press the button, then I would still get an output of 0. Because I haven't put in any money and I've just pushed a button to try and get my coffee. So what case will we get a 1 coming out here? So if we set up my AND gate, if I was to push, so this is coin, we'll just call it C and B. If I was to put in a coin, that would stand as a 1. And if I was to push the button, I'd also get a 1, and that means I'll get a 1 as an output, and that is known as an AND logic gate. In summary, it's only 2 1s will give you a 1 on an AND gate. So the next thing I'm going to show you is how to draw a truth table with that. So a truth table is going to look as follows. If I was to label these just for simplicity, A, B, and C. B and C. And if I was going to give all the possible inputs that I could get in here. So the first one is we could have 2 zeros, which would mean there's no coin put in and there's no button pressed. The next one we could have would be 2 1s, which means I put in a coin and I press a button, in which case we know that it will get coffee out of the machine. And the other one would be a 1 and a 0. So that means A is going to be 1, B will be 0, and then a 0 and a 1. So let's look over. What are we going to get at C? So we said, in summary, it's going to be just these 2 1s that will give us a 1. So 2 1s will give us a 1. So that means an output, meaning that the machine will turn on. And if there's a 0, the machine will not turn on. So the other ones will be all 0, 0, 0. And that's your truth table for an AND gate. Now the next one we're going to look at is an OR gate. Actually, sorry, to finish up with the AND gate, I'm just going to show you what would that look like in an electric circuit. So in an electric circuit, we'd have our plus down here. We'd have 2 different switches. A negative, and sorry, I'll put in a bulb here as well. So that's the symbol for a light bulb. What happens if I close in this switch? I'll just get a different color pen for this one. So what happens if I close this switch? Will electricity flow? No, because there's still a gap here and electricity cannot make a full circuit. So if I close 1, that'll give me a 1 and a 0. Nothing's going to happen. The bulb won't turn on. What happens if I close both switches? Then we'll get 2 1s, which will give me a 1 at my light bulb. So that's the same as, that's our AND gate represented in a circuit. Now the next gate I'm going to show you is a OR gate. So an OR gate looks like this. What would we use an OR gate for? Well, could you imagine if we had a house and there was a doorbell at the front and there was a doorbell at the back? And we wanted a situation where if we were to push either of these, the doorbell would ring. Or if we were to push both of them, if there was somebody at the front of the house and there was somebody at the back of the house, the doorbell would also ring. So how do we represent that with ones and zeros? So if we have if somebody pushes the front doorbell, somebody doesn't push the back doorbell, what would you imagine would happen? Well, the doorbell will ring. What happens if somebody pushes the back doorbell and pushes the front doorbell? Then the doorbell will ring. What happens if somebody doesn't push either of them? Nobody's pushing any doorbells. Then you could imagine that the doorbell won't ring, in which case we'll have a 0. What happens if somebody pushes both of the doorbells at the same time? 2 ones. What will we get out here? If somebody pushes the 2 of them, we'll also get a 1. So we'll look over the truth table similar to the one we have here for our AND gate. We'll do a truth table for our OR gate again. I'll redraw the OR gate and we'll label them just like the last time. We'll label them A, B and C and we'll draw out the truth table for that. So A, B, C, and we'll again draw all our different combinations. So we can look same as our last table. We're going to have 2 zeros, a 1 and a 1, a 0 and a 1, and a 1 and a 0. And these can be in any order. You could start off with 2 ones on the top. You could have a 0 and a 1 second. It doesn't matter. Just have them in any particular order. And we're going to look at what happens. If we don't press the doorbell, we get 2 zeros in, we're going to get a 0 out. If we press both doorbells, we're going to get a 1 out. If we press only B, so we press one doorbell, then we're still going to get the bell will ring. If we press the other one, it's also going to be a 1. So you can see on our OR gate, everything is going to give us a 1, except in this case, 2 zeros. Every other option will give us a 1. How a OR gate looks when it's actually in a circle will be like this. So you have your plus going down and your circuit will branch off into 2 paths. There's your bulb symbol. So your electrons are flowing from your positive down to negative. Now, if you close one switch, you can see that the electricity will have a path to come down through here, lighting up the bulb. If you close the other switch, it can go down this side, lighting up the bulb. If you close both switches, then electricity can come down, go through your 2 switches and light up the bulb. So you can see a 1 and a 1, 1 meaning the switch is on. A 1 and a 1 will give you a 1 out here. 0 and a 1 will give you a 1. 2 zeros, 2 open switches, electricity can't get down. You'll get a 0 there. Now we're going to look at one final gate before I show you how to combine different ones. And that's the simplest gate there is, and that is called a NOT gate. And that could be used for something like a burglar alarm. If you had a burglar alarm where you had a continuous circuit that was connected together, and when that circuit was broken, we want to get a 1 output so that we set off our burglar alarm. So a NOT gate is very, very, very simple. It works by simply taking a 1 and turning it into a 0. Or if we have a 0, turning that into a 1. Now, what does the truth table look like for a NOT gate? Very simple. It's only going to have an input. It's only going to have 1 input and 1 output. So instead of having 3 here, we're only going to have 2. A and B down. What happens when we get a 1 into A? We get a 0 out of B. What happens when we get a 0 into A? We get a 1 out at B. Now, the next time I'm going to show you what will happen if we combine different parts of these logic gates. So say if we wanted a system like so. We start off with an AND gate. What do we need for an AND gate? It's only 2 1s will give me a 1 out of an AND gate. So try and remember that. We connect that into an OR gate. And let me see, I'll put a NOT gate on this point here. We've got 3 different inputs, A, B, C. Then we're going to have a point D here, E. So these will be going directly into this, and then we're going to have F as our final output. So we're going to draw our truth table to see what that looks like. So what happens, it's only going to be, just in summary, it's going to be 2 1s will give us a 1 out here. Everything else will give us a 0. If there's any 1 signal or 2 1s going into this, we'll get a 1 out. The only time we can get a 0 here is if there's a 0 here and a 0 in this point. So what will the truth table look like? It'll look like so. A, B, C, D, E, and F. So there's going to be loads of different combinations between these. There'll be actually 8 in total, and I'm just going to do a couple of them just so you can get the gist of it. If you're doing a question in Junior Cert Technology, where they combine logic gates, they typically won't just get you to draw the table from scratch. They'll actually ask you to, they'll give you a number of combinations of 1s and 0s for these inputs, and they'll ask you to give your outputs. So I'll start off with a couple of different ones. Let me see. We start off with 3 0s, all 1s, 0, 1, and a 0, 1, 0, 0, and I'll do one more. 1, 1, and a 0. We'll see what we get out for them. So for our first one, we'll start off with it here. We've got 2 0s in A and B. So this is our AND gate. Remember, D is going to be our output for A and B. So we could actually do all of these together, but I'll just do them one at a time. You could see that A and B will give us out at D a 0. An AND gate will only give us a 1 if we've got 2 1s coming in. So I'll do them all down in a row here. If we take for the second case, 2 1s will give us a 1. A 0 and a 1 for an AND gate gives us a 0. A 1 and a 0 gives us a 0. A 0 and a 1 gives us a 0. So if you look at, we've all our combinations filled in for our AND right down through our truth table. You can do these one at a time. I find it easier to do them all together so you can keep them going. The next one, C. If a 1 comes into C, a 0 comes out to E. It's just going to be the opposite. That's why it's called a NOT gate. So we look at our combination C this time. C, you get a 0 in, 1 out. 1 in, 0 out. 0 in, 1 out. It's just going to be the opposite one here. So 1, and then we'll get a 0. Our final one, F. So for F, we're going to be taking D and E together. So an OR gate, you remember that if we get 2 1s, we'll get a 1. If we get a 0 and a 1, we'll get a 1 out. So let's look at the two of these together. 0 and a 1 will be a 1. A 1 and a 0, a 1. 0 and a 1, a 1. 0 and a 1 is a 1. 2 zeros together are the only combination for an OR gate that will give us a 0. So in that case, we have a 0. So the 3 gates we've looked at so far are our AND gate, our OR gate, and our NOT gate. So an AND, 2 1s will give me a 1. Anything else, a 0 and a 1, 2 zeros. Anything else will give me a 0 out here. An OR gate, you've got, if there is a 1 going into either of these or both of them, you're going to get a 1 out here. So a 1 and a 1 will give me a 1. A 0 and a 1 will give me a 1. 2 zeros are the only one that will give me a 0. A NOT, whatever comes into it will change. So 1 will come out as a 0, and a 0 will go in and come out as a 1. There's 2 other gates that you need to know. And if you can understand the three of these, they're actually not too hard to understand. And that is a NAND and a NOR. What are the two of these? Well, these are these gates followed immediately by a NOT gate. Or if you want to think of it as the opposite of what you normally get out of these. So I'll give you an example. A NAND gate looks like this. It's a AND gate just with a little ball there at the top of it. That's a NAND. Or if we want to draw it this way beside it, it'll be an OR gate. Now remember, these are the same thing. It could be also an OR gate, an AND gate, immediately followed by a NOT gate. So what will happen in an AND gate? Say if we just take one example, we get two ones coming in here. The only one that will normally give me a 1. So 2 ones gives me a 1 at this point. If we were to immediately put that into a NOT gate, it would reverse that signal and we get a 0. So in a NAND gate, 2 ones gives me a 0. Similarly, if I change this to a 0 and a 1, what will we get for a 0 and a 1? We will get a 0, because it's only 2 ones will give me a 1 here. If we put that into a NOT gate, it'll come out as a 1. So in a NAND gate, a 0 and a 1 will give me a 1. What does the truth table look like for that? Well, it looks like this. A, B, C. A, B, C. We'll list our 3 different combinations. Uh, 0, 0, 1, 1, 0, 1, and 1 and 0. Two zeros normally gives me, and if this helps you, in an AND gate, it would normally give me a 0. But in a NAND gate, it's going to give me the opposite of that. So 2 zeros normally gives a 0 in an irregular AND gate, but in a NAND gate, it's going to give me a 1. 2 ones in a regular one will give me a 1. In a NAND gate, it'll give me a 0. 0 and a 1 usually gives me 0, but in a NAND gate will give me a 1. Now these parts here are just reference. You don't have to draw these in, but they can help you when you're trying to think about it. A 1 and a 0 normally gives me a 0, so in this case it gives me a 1. Now if you can understand a NAND gate, then and you understand an OR gate, then you should be able to figure this out too. So I'll show you. An OR gate, a NOR gate looks like this. It's just an OR gate with a little ball drawn here on top. And it's the same thing. It's similar to an OR gate followed immediately by a NOT gate. So what do we know about an OR gate? We know that if we got a 1 and a 1 into it, 2 ones, what do we get out? We get a 1. What happens if that goes immediately into NOT gate? We get a 0. What happens if we get 2 zeros? 2 zeros will give me a 0 out. This is the only one. It's only if we get 2 zeros in this we'll get a 0 out. Everything else is 1. If a 0 comes in through here, gets flipped by a NOT gate, and we get a 1 coming out of it. So let's draw the truth table for that. Again, A, B, C. We'll draw all our different combinations there. So a 0 and a 0, 1 and a 1, 1 and a 0, and a 0 and a 1. So, normally in an OR gate, a 0 and a 0, again I'm just drawing this in for a reference, you don't have to draw this in, but it might help you. A 0 and a 0 will normally, on a regular OR gate, give me a 0. So what happens in a NOR? That gets flipped around and we get a 1. A 1 and a 1 will usually give me a 1. A 1 and a 0 will usually give me a 1. and a 0 and a 1 will usually give me a 1. Let's flip them around. A 1 flips to a 0, a 1 flips to a 0, and a 1 flips to a 0. And they are the main logic gates you need to know, and the truth tables associated with them.